All right, guys, we're going to continue talking on our ultimate subject of electrochemistry, but with an emphasis today on, we talked about redox reactions, but electrolysis. Okay, so psychic hotline, two guys talking. You're fine. How am I? So psychics talk to each other. Okay, guys, this is, I don't know if you guys can see, it's a galvanic cell. You guys, that's another word for a voltaic cell. So I want to, this is a little review.
A galvanic cell is a spontaneous electrochemical cell in which electricity is produced by means of a spontaneous redox reaction. In this cell, zinc metal will be oxidized and copper 2+ ions will be reduced. To complete the electric circuit, the solutions must be connected by a conducting medium through which the cations and anions can move. This requirement is satisfied by a salt bridge, which in its simplest form is an inverted U-tube containing an inert electrolyte, such as sodium nitrate or potassium chloride.
See, that's ultimately allowing electrons to travel through, which is generating a voltage that says 1.1 volts. So now we'll kind of look at
the zinc electrode, zinc metal is oxidized, losing 2 electrons to produce zinc 2+ ions. At the copper electrode, copper 2+ ions are reduced, gaining 2 electrons to produce copper metal. Electrons flow from the zinc electrode to the copper electrode. The zinc electrode is dissolving to zinc 2+ ions over time, and copper metal is building up on the copper
building up.
Click on one of the buttons to view that portion of the galvanic cell on a microscopic scale.
Okay, so then we can kind of see what's happening. Remember, at the anode, that's where oxidation is happening. Zinc is being oxidized to zinc 2+ ions.
At the zinc electrode, zinc atoms are losing 2 electrons, forming zinc 2+ ions, which enter the solution. The 2 electrons lost by zinc metal flow through the wire to the copper electrode. Note that only zinc 2+ ions are shown in solution. Other ions and water molecules are not shown to focus on the oxidation of zinc metal to zinc 2+.
So hopefully you guys could have seen that, right? Zinc was being oxidized to zinc 2+, so you're having a buildup of the zinc 2+ ions here in the solution, making this solution, if you didn't have a salt bridge, making it positive, okay? But now we're going to see what will the salt bridge allow to happen so that you won't have a buildup of charge.
The salt bridge contains sodium nitrate, which exists as sodium ions and nitrate ions in solution. As the zinc electrode is oxidized to zinc 2+, a positive charge builds in the solution due to the zinc 2+ ions. If this positive charge were not counterbalanced, the galvanic cell would cease to function in a short period of time.
See what happens?
The negative nitrate ions flow into the solution containing the zinc electrode, and the positive zinc 2+ ions move in the opposite direction to balance the charge.
See, otherwise there'd be a buildup of zinc 2+ ions. But what's happening is the negative nitrate ions are coming in and stabilizing that, so there's not a buildup of positive charge. And then I could show that on this other side, right, with copper 2+ ions being reduced to copper, you're having positive ions coming out of solution, and so then you would have more of these negative nitrate ions. So then what will happen is positive sodium ions can come here and stabilize the increase in the negative charge, thus keeping these, the whole purpose of the salt bridge is to keep these solutions neutral, so therefore the electrons continue to flow from the anode where oxidation happens and electrons are lost to the cathode where electrons are gained. So look what's happening on the copper end.
Electrons formed at the zinc electrode travel to the copper electrode. 2 electrons combine with each copper 2+ ion in solution to produce copper metal. Note that only copper 2+ ions are shown in solution. Other ions and water molecules are not shown to focus on the reduction of copper 2+ to copper metal.
All right, guys, move along. Okay, so you guys remember what we were saying with galvanic or voltaic cells? Same thing. Those are essentially batteries. So, like for example, this is like a car battery, and you guys should associate car batteries with, right, battery acid. You have sulfuric acid is actually the battery acid here. So you have these series of lead. Notice you've got lead oxide, and you have some other pure lead. Here's kind of what's happening. So in a car battery, for example, so you have this lead oxide. Notice, you guys remember you assign oxidation numbers. Oxygen's -2, so if there's two -2s, that means the lead is +4. So you guys see in this situation, the lead, it has a +4 oxidation. Now you're forming lead 2+ ions, which is the same as oxidation number. Notice what's happening to the oxidation number. It's getting smaller. That means the lead is gaining electrons. This is being reduced. You guys remember, wherever there's a reduction, there also has to be an accompanying oxidation. And then you also have lead, right? So this is the reduction half reaction. You also have pure lead that's being, notice, look, you guys remember pure elements have an oxidation number of 0. It's being oxidized from 0 to +2. That means it lost electrons, right? It'd be 2 electrons here. So you have an oxidation reduction. And remember what they do is we keep it separate so those electrons travel through, right? It's going to be from the negative terminal, which is which we call the anode. That's where oxidation occurs. Electrons are lost, and then they're going to pass through your car and run the different systems in your car to the positive electrode where the electrons are gained. That's where reduction happens. Okay, now notice this, how you guys look how batteries work. You guys remember we said in our typical batteries, AA, AAA, these, all those, they're really 1.5 volt batteries. So how are we going to get a higher voltage? What you can do is you put it in series. So you take these batteries and you put them end to end, and you can see what ultimately the voltage is. You see what you do. If you take two 1.5 volts and you put them in a series connection, they call that a series end to end. The voltage is additive. That's how we get 3 volts, which is what would probably be necessary to power that flashlight. Look at this. This is like your watch battery, right? If you have a typical watch, where else would you have that? A calculator. This could be a battery. You guys, it's the same thing. You've got an anode and a cathode, and what you do is you keep them separate. So then the anode here, you guys remember what happens at the anode? That's oxidation. That's where electrons are lost. Oxidation is lost. So the electrons are lost here. You guys see you put this in your watch, and so the electrons are forced through your watch. They're attracted to the positive end, whereas that's the cathode where reduction occurs, where electrons are gained. Okay, so just different variations of a battery. You guys, this is kind of an interesting thing. This is actually very current. You guys, right, we talked about electric cars. There's also hydrogen fuel cell cars. And you can see what the good thing is about this. And basically, it uses a pretty simple reaction. Basically, it takes the combustion reaction of hydrogen and oxygen, and those combust together to form water, and that's also the same reaction that propels the rocket in outer space. But usually if you just allow this to happen on its own, it's just going to produce a lot of heat, right? But a lot of times that's going to be wasted. But if we can separate out, you guys, and look at what's happening here, right? These both have an oxidation number of 0. You guys remember pure elements are 0. And then in water, oxygen is -2, hydrogen is +1. So oxygen here, or I'm sorry, hydrogen here, notice it's being oxidized, going from 0 to +1, had to have lost electrons. And then oxygen here, going from 0 to -2, it's being reduced. So what we do is we separate out those half reactions. So here's how a hydrogen fuel cell works. We pump in hydrogen and we pump in oxygen, but once again, we're allowing these to be separate. So then the oxygen will be reduced, the hydrogen will be oxidized, ultimately. And you guys, the benefit of this and using this reaction, which is a very highly energetic reaction, the benefit is what comes out of the exhaust. You might have some excess hydrogen oxygen that was unreacted, but really the only product of this reaction, or you don't have carbon dioxide and other global warming gases, you just have water. And you can see for this, the cell potential for this hydrogen fuel cell is 1.23 volts. You guys can imagine, you're not gonna be able to power a car on 1.23 volts, maybe a little Hot Wheel. So what do? You would stack a bunch of these, like we were saying, in series, and you would add those all up until you got the, certain, voltage that you needed to drive your car. Here's another example of oxidation reduction redox. You guys, simple rusting is a redox reaction, right? You guys think about iron, right? And you know what? A lot of times we associate rusting with water. You don't need water. Water's not necessarily a reactant in the rusting process. When you have rusting, basically what you're having is you're having iron reacting with oxygen to form iron oxide. The water, all water does, it serves as a catalyst. It just causes that reaction to happen faster. But here's kind of really what's happening. You got your iron being reduced, right? Think about your pure iron. It's being reduced. I'm sorry, it's being oxidized, as you would expect metals to be. They're being oxidized. And what's it being oxidized? It's being oxidized typically by oxygen. You guys remember that's why we call it oxidation, because it's based on oxygen tends to oxidize others, and because oxygen in this case is being reduced. Look, oxygen with four electrons. So, question is, I would ask, have you guys heard of? Well, first of all, when you talk about metal, a typical metal that we use is steel. Steel is really strong, and the primary component of steel is iron. But what's the problem with iron? Iron tends to rust. So there's a technique we use. We galvanize that steel. Maybe you guys have heard of galvanized steel. A lot of pipes, under homes, older homes, could be, they don't have the copper pipes or now the PVC pipes, would be galvanized steel. Here's what galvanized steel is. Basically, it's just taking your steel, which is primarily iron, and you're coating it with zinc. And here's the reason. You coat it with zinc, and what you're going to do is you're going to protect your iron. So check this out, guys. Look. So this is showing the reduction. You guys remember we have a list of reduction potentials. We can look up the reduction potential of iron is negative 0.44. The reduction potential of zinc is negative 0.76. You guys remember what the negatives tell you? That the reduction of these metals is not spontaneous. What's spontaneous is the reverse reaction in which those are being oxidized. So what we want to do though is see which one of these is more likely to be oxidized. So what you would do is you compare the reduction potentials, and you notice for zinc, it's got a lower reduction potential than iron. So what they're saying is zinc is less likely to be reduced than iron. And the lower the reduction potential, what does that mean? The more likely the reverse reaction, the more likely it is to be oxidized. So this would indicate that zinc is more likely to be oxidized than iron. So therefore, when we have iron pipe that we want to protect, because iron's really strong, that's why we use it for steel, we would coat it with zinc. That's what you call galvanizing, because then when exposed to oxygen, which typically oxidizes things, it's going to oxidize the zinc before it oxidizes the iron. Okay, now this next thing we're going to look at is an example of electrolysis. This is the new topic. Okay, not initially, but I'll show you when it changes. Okay, so check this out. Okay, so here basically we have our voltaic cell set up, right? You guys remember we've seen this before, zinc and copper. Zinc will be oxidized to zinc 2+, and then the copper 2+ ions will be reduced to copper, okay? And what we're showing is we have a 1 gram electrode of zinc and a 1 gram electrode of copper, so we'll just start the reaction. And you guys can see electrons are flowing from the anode to the cathode. So this is your typical voltaic cell. This is a battery. So what we're saying is it's being discharged, right? And the battery, you guys remember, will keep going until what point? Until we run out of the reactants. Either the zinc electrode is going to break up, or we run out of the copper 2+ ions that are being reduced. And you notice we have a salt bridge which allows positive and negative ions to go back and forth to stabilize the charge on these okay, so now look at what we're doing different. Now this is different. Now this is now describing an electrolytic cell. Notice the little hamster wheel. Basically what he's doing is he's inputting energy. Remember the other reaction, it was the voltaic cell was causing the electrons to flow. Now what the hamster is representing, it's like a power source. What the power source is doing is causing the electrons to go in the opposite direction. That's what we call electrolysis. An electrolytic cell is a cell in which you use a power source. This is kind of little joke here, but you use a power source to get a reaction to go in reverse. Because right, the reaction going in reverse is not spontaneous. You would need to input energy in order to get that reaction to go in reverse. That's what we mean by an electrolytic cell. So a voltaic cell, you can think of it as a battery, generates electricity by causing electrons to flow, right? This is the discharge of a battery. But then, ultimately, guys, that's what we're talking about. That's essentially what you're showing on a rechargeable battery. How do rechargeable batteries work, right? Rechargeable batteries, electrons will continue to flow until you run out of reactant species. And then what do? You take that rechargeable battery, you put it in a battery charger. What does that do in the battery charger? Here, we'll flip it. It now inputs energy. And what can we do? We can get the process to go in reverse, thus replenishing the original reactants we had, so that way that battery can be used over and over again. Okay? Okay, you guys, this is very important. Write these notes down. This is going to help us ultimately we're going to need to know these values when we solve problems, which we're going to end solving a problem here shortly. So just note this, charge on 1 mole of electrons. You guys know electrons, we don't talk about individual electrons, we'll usually talk about moles of electrons. You got to remember a mole is 6.02 times 10 to the 23rd. So a charge on the mole of an electron is 96,485 coulombs. So that, you remember coulomb is a measure of charge. We call that 1 Faraday. Remember there was Faraday's constant? So Faraday's constant, right? So this is how you write it. Faraday's constant is 96,485 coulombs per 1 mole of electrons. And so what we could do is we could rearrange this. We would say, let's say, remember it's per mole. So let's say I bring this here, multiply both sides by mole of electron, then divide by Faraday's constant. A mole of electrons is equal to whatever your total charge is divided by your Faraday constant. So that's just a way you could manipulate that. Note this, 1 coulomb of charge is the quantity of charge passing a point in a circuit, right? A circuit's just where the path where the electron flows. Every second when there's a current of 1 ampere. You guys have heard of amps. Amp is a measure of current. So here's how we could show that. So rearranging this, we could just say a current is equal to the charge per second. When we're talking the current, we're saying how much charge is passing along that current every second. And so here's an abbreviated way. We use I as an abbreviation for current. Q is an abbreviation for charge, the amount of charge. And then T, as you might expect, would be time, but it's time in seconds. Okay, so you guys, we're going to finish with a problem here, and you know, there's going to be multiple steps, and that's kind of what makes this difficult. But hopefully, with this and you know, practice, we'll get this down. Okay. I know it looks like a lot, guys. Let's see what we got here. Here, I'll leave that up. Okay, so here's the question. You guys write this down. Say we have 10 amps are passed through molten aluminum chloride for 5.5 hours. Okay, so we're passing a current. So basically, and I even drew a picture. In fact, I would advise you guys to draw pictures just to kind of see what's going on. So we have this molten. So molten means we have aluminum chloride, which would normally be a solid, but you heat it up and it's now a liquid. The question is, how many grams of aluminum metal could be produced by electrolysis? So what this is showing is a way by which, for example, let's say, you know, you guys remember we were saying most things don't exist as pure elements in nature. In fact, aluminum might be found as an aluminum oxide, or in this case, an aluminum chloride. So we can use the process of electrolysis in order to acquire pure aluminum from aluminum chloride. Now, we're going to look at why do we need the process of electrolysis to do this. Okay, so now let's look at this. First of all, you guys remember we want to look at an equation, want to see, okay, is this a redox reaction? Remember how to do that? You assign oxidation numbers. Chlorine is -1, there's 3 for every one of this, so aluminum plus 3. Here's pure aluminum, that's a 0, and that's pure chlorine, that's a 0. Now you guys look, in this reaction, aluminum's going from a +3 to a 0, so it's being reduced. It must be gaining electrons, and the chloride's going from a -1 oxidation number to a 0. The number's getting bigger, therefore it must have lost electrons, it's being oxidized. So now we want to see, okay, could this reaction happen? Okay, we want to see, could this reaction happen? So we have this aluminum chloride here. Now think about, so remember we're always going to separate the half reactions. So at one electrode, you would have the, we're showing the the reduction of aluminum. See how it's gaining 3 electrons. Basically, this was writing the half reactions, and so we just kind of skipped it and wrote the half reaction for this. And so here, this is showing aluminum being reduced, and this is showing the chloride ion being oxidized, okay? So now, we want to see, could this reaction happen? Would this reaction be spontaneous? Remember how you can do that? You can look at the reduction potentials. So, you guys would look on your reduction potential chart, so then I would look for chlorine, and I'm seeing the reduction potential for chlorine is plus 1.36, okay? Then I look at the reduction potential for aluminum, it is negative 1.66. But in this reaction, the aluminum is being reduced. You guys see that? The aluminum is being reduced. The aluminum is gaining electrons to become pure aluminum. So I would leave that. But if aluminum is to be reduced, obviously the chlorine has to be oxidized. But you guys remember, this is the reduction potential. So how would I show the reverse? So if the aluminum is being reduced, the opposite reaction is happening for chlorine. chlorine is being oxidized. So what does that do to the value here? If this is a positive 1.36, which means that it's spontaneous this direction, what does it mean about the reverse reaction? Did you guys notice this is the reverse reaction than that? It's the opposite. So it's negative 1.36 volts. So if this is being oxidized and then the aluminum is being reduced, you remember how we get the overall cell potential? You take the oxidation potential plus the reduction potential, and what will you notice when you add those together? You're going to get a negative 3.02 volts. What do you guys notice with the overall cell potential? The overall cell potential is a negative. What does that tell you? That is not spontaneous. That reaction won't happen on its own. But can we get that reaction to happen? Yes, if we input energy into the system. And so in this case, it's not going to be a voltaic cell, which generates, energy via the spontaneous reaction, the movement of electrons via a spontaneous reaction. This is going to require energy to get a reaction to happen that wouldn't otherwise happen. That's what we call an electrolytic cell. So in this case, you notice here, notice this isn't a voltmeter. It's not showing how many volts are being produced. It's a power source. So you're actually hooking up a battery or another power source, and you're causing the electrons to flow, right? When the electrons flow from the negative terminal, right, they're going to be attracted to the positive terminal. But now we're causing those electrons to travel here. So then the electrons would come through this electrode, which is the cathode, where you guys remember cathode is where reduction occurs. So aluminum ions in solution, so you have this aluminum chloride. So aluminum ions in solution are gaining these electrons and then forming pure aluminum. So what would you guys see forming on the outside of this electrode? Pure aluminum. And then, right? And then what happens is the negative chloride ions that are in solution are being oxidized, and thus, right, and losing electrons, and then those electrons that are lost are attracted to the positive terminal, and so then you have that going. So the question is, overall, how many grams of aluminum, where are we at? Okay, I got a few more minutes. How much aluminum can I produce? So you guys, this is a reaction that we would use in order to acquire pure aluminum. You guys, back in the day, right, we always know silver is valuable, gold's valuable, but back in the day, hundreds of years ago, they never knew how to get pure aluminum. So you could argue that, hundreds of years ago, aluminum was more valuable than gold or silver, because gold or silver, you guys remember, it's pretty non-reactive metal. You can actually find pure gold and silver if you mine it. But aluminum's so relatively reactive, you're not going to find it as a pure element, you're going to find it as a compound, but they didn't have the chemical means by which to, easily acquire it. So anyways, let's say we could use an electrolytic process. Let's say we're making silverware and we wanted to aluminum coat it. Well, we could use an electrolytic process, and we could put, for example, a spoon or something like that and collect aluminum. The question ultimately is, if this power source is creating 10 amps, it's a 10 amp power source for 5.5 hours, how much aluminum would I produce? So let's start with what we have. We got 10 amps for 5.5 hours. Basically, I'm going to be able to figure out how many electrons are passing through here in that given time. You guys remember 10 amps? So that amps is a charge per time. So 10 amps is like 10 coulombs per second. That's right, because that's essentially what an amp is. 1 amp is a coulomb per time. So, and notice it's for 5.5 hours, but look, it's got 10 coulombs per second. So what am I going to want to do? Here, you know what? Let's go with this. Ultimately, I'm going to want to convert 5.5 hours into seconds. So basically, here's what I can do. I could go, so 5.5 hours. You guys know there's, how should we do this? Should I just do it for you or what? Let's go, so it's times, okay, so we got 10 coulombs per second, that's what the 10 amps is, for 5.5 hours. But obviously, we've got, we want to do some conversion here. So I got 1 hour is 60 minutes, hours cancel, and 1 minute is 60 seconds. You guys see what we're going to do? And look, second on top, second on bottom is going to cancel, and ultimately I'm going to get how many coulombs. So I'm going to go 10 times 5.5 times 60 times 60, and what do I get? I get 198,000 coulombs. Okay, so that's what you guys remember, coulombs is the amount of charge, okay? Then we can use Faraday's constant. You guys remember Faraday's constant? Was it 96,485, if I can remember correctly, coulombs for every 1 mole of electrons. That is a constant that we use. So then I can ultimately use the amount of charge, use Faraday's constant to figure out how many moles of electrons travel through here in 5.5 hours, and that's 2.05 moles of electrons. You guys remember, and ultimately what I want to figure out is how much aluminum am I going to produce? Well, you guys see, for every 1 mole of aluminum that's produced, 3 moles of electrons has to reduce this. So it's a 1-to-3 ratio. So basically I'm going to take my 2.05 moles of electrons and use this ratio here. 3 moles of electrons are required for every 1 mole of aluminum that is produced. So basically I'm going to take this value and divide by 3, and I do that, and I'm going to get 0.684 moles of aluminum. So that's how much aluminum I produce. But you guys know we usually don't want to talk about moles when we're talking about the amount of aluminum. We probably want grams. So the last thing I would do is take that 0.684 moles of aluminum and see, well, how many grams. I use the molar mass of aluminum. Look on the periodic table I'm looking now. It's 27 grams per mole. So 27 grams for every 1 mole. Moles cancel. 27 times 0.684, and I get 18.5 grams of aluminum. And you guys see, that's a pretty expensive, aluminum's kind of expensive, relatively, to make. It would take a 10 amp power source to run for 5.5 hours through a molten aluminum chloride solution just to generate 18.5 grams of aluminum. So once again, guys, this is an example of an electrolytic cell. Once again, the biggest difference between it's almost the exact opposite. A voltaic cell, think about it as a battery that generates a voltage due to the spontaneous movement of electrons. An electrolytic cell is one in which you have to use a power source to cause a non-spontaneous reaction to occur. All right, well in there, guys. See you.